So during our investigation in the last section, we found that derivatives split up really nicely over sums and differences. Now when it comes to products and quotients, however, well, the bad news is that it doesn't work out quite so nicely. But the good news is we can still come up with useful formulas for tackling them. And we'll actually come up with one rule for products and a different rule for quotients. So we're going to start with the product rule. So we're going to start with two functions, f and g. And as I've used this language in the last section, I'll just remind you what I mean when I say let f and g be differentiable functions. Let's just say they're functions whose derivatives you can take. Right? You can use the limit. You can use the limit definition of the derivative, or maybe it's the power rule, or maybe some other property, but somehow you can come up with a derivative for these two functions f and g. That's what we're assuming in the background. But now I'm going to form this new function, capital F, by multiplying those other two functions together, which I've written here. So capital F is the product function. And what we're going to do is come up with a rule for the derivative of capital F, the product function. So how are we going to do that? Well, we don't have a rule for products yet. So remember what we do whenever we don't have a rule for a certain type of function? Well, we automatically use the definition of the derivative. So we're going to have the limit as h goes to 0 of capital F of x plus h minus capital F of x, all divided by h. Right? So that's just applying the limit definition of the derivative for the function capital F. But now let's use the fact that we have a definition for capital F, right? It's the pointwise product of little f and little g. So really what this means, I'll just remind you, this means that capital F of x is really equal to little f of x times little g of x. That's what it means. That's what it means to define a product, or to write down a product like this. It means that this is how your capital F function is defined. So this is how we can actually work out what these two pieces are on our next step. So this is going to be the limit as h goes to 0 of little f of x plus h times little g of x plus h. So really, what I've got so far, what this is just this first term in the numerator. It's capital F of x plus h. But now we're going to subtract capital F of x, so we're going to go minus little f of x times little g of x, and this is all over h. So all we've done now is we've unwound what the function capital F actually does. And then, well, now it looks like we're just at a brick wall. I mean, what are you going to do here? You can't plug in h equals 0. What happens if you try to plug in h equals 0? Well, this would just become f of x, and this would just become g of x. So you've got f of x times g of x, but then you subtract f of x times g of x. So you'd end up with a 0 over 0 type. So just plugging in h equals 0 at this stage isn't going to work. Now we do have a hidden assumption that we haven't used, and that is that the function little f and the function little g, they're both differentiable. They have derivatives that we can write down. But it's not obvious how we're going to use that here. And it's actually a trick. And once you see it, it's easy to see it after it's done and say, oh, that's neat how that worked. But until you see the trick, it's not so obvious what to do here. So I'm going to show you the trick. It actually comes down to adding, but then subtracting something right after. So you're not actually changing it, because as soon as you add something, you also subtract it immediately after. So it's like adding 0, but it just turns out to change the form of things so that everything works out quite nicely. So here's what we're going to do. So the limit as h goes to 0, I'm going to write the first term down. So f of x plus h times g of x plus h. And now what I'm going to do is I'm going to subtract f of x times g of x plus h. But then, if I subtract that, I can't just randomly subtract something and still be working with the same expression. So before I subtract this f of x times g of x, I'm going to add this back on. So I'm going to go plus f of x times g of x plus h, and then I'm going to go minus f of x times g of x. Okay, and all of this is divided by h. So you can see the only difference between these two steps are these two middle terms that got inserted. But really, they cancel out anyway. If I wanted to cancel these out, I would just be left with this term and this term, which is exactly what I had at the previous step. Of course, I'm not going to cancel them out, because if I did that, well, I would just be going backwards, and I would be back where I started, and this would have been a waste of time. So instead, what I'm going to do is I'm going to split this up into the sum of two fractions, taking advantage of fraction properties. So this is actually the limit as h goes to 0. So I'm going to copy the first two terms down f of x plus h times g of x plus h minus f of x times g of x plus h. Okay, so that's the first two terms. And then I'm going to divide that whole expression by h. So really what I've got is these first two terms divided by h. But now I want the second two terms divided by h for my second fraction as well to make sure that this is accurate. So I'm going to write this as plus f of x times g of x plus h minus f of x g of x all over h. Okay, so that's how we can split that up. And then now what I'm going to do is I'm going to factor out any common factors from these two terms in the numerator, and then I'm going to factor out any common factors from these two terms in the numerator. So what's that going to look like? I'm going to have the limit as h goes to 0. Well, if I pull out, what's the common factor here? Well, this term has a g of x plus h, and this term also has a g of x plus h. So I'm going to pull that out. I'm going to say g of x plus h multiplied by f of x plus h minus f of x, and all of this is over h. And then what do we have? The limit as h goes to 0. And what do we have here? Well, we have a common factor of f of x. So we get f of x multiplied by what will be left? We'll just have g of x plus h minus g of x. And then, of course, all of that is divided by h. I'm running out of space here. I better slide this up. Okay, and now what? Well, I can really split this up over two, or split this up as g of x plus h. That can come right out of the fraction and be multiplied out in front of it. Same with this f of x. This f of x can be pulled out of the fraction as well. So not much is going to change here, but it is an important step to make this actually work out. So we've got g of x plus h. Now I'm going to multiply this by the same, multiply the g of x plus h by the entire fraction f of x plus h minus f of x all over h. So that's this fraction just written a little bit differently with this factor of the numerator just pulled aside out of the fraction like that. And then the next one I'll have the limit as h goes to 0. So I'll pull the f of x out of the fraction, and I'll have g of x plus h minus g of x all over h. Okay, and I'm going to now, we're almost done. We need to do one more key step and then we're done. Now I'm going to use the fact that limits respect products, in the sense that if I have the limit of a product of two functions, I have a function here and a function here. For any fixed value of x, which is how you should think of x at this stage, it's a fixed value. It's the point at which we are trying to write down the derivative of the function capital F. Okay, so this really the variable in the function variable as far as the limit is concerned is the variable h here. So this is a function of h and this is a function of h. Well, and they're being multiplied inside the limit. Well, we can split that up as a product of two limits. So this is going to be the limit as h goes to 0 of g of x plus h times the limit as h goes to 0 of f of x plus h minus f of x all over h. So I just took this one limit and split it up into the product of two separate limits. And then here, hope I don't run out of room, and the second part we'll do the same thing here. This is a function of h. It's a constant function of h because x is independent of h, and then this is a function of h. So we'll split this up into the product of two limits as well. So we'll have the limit as h goes to 0 of f of x multiplied by the limit as h goes to 0 of g of x plus h minus g of x all over h. And now we're ready to wrap this up because it's all set up quite nicely. We've got four limits, and these are all actually, to be consistent, I'll just put brackets here. These are all going to be quick to identify. because let's start with this one. Okay, let's start with this one here. The limit as h goes to 0 of g of x plus h. Well, what's happening as h goes to 0? Well, this little piece here that you're adding on to x inside the function g, this is going to disappear. And really, you're just going to end up getting g of x. Or g of x, pardon me. So that's just equal to g of x. What about this limit? This should be actually familiar. This is a very specific limit. This is exactly the limit that appears in the definition of the derivative of little f. Right? This is literally what, if I gave you a function little f and I said write down the definition of its derivative, this is what I would expect you to write down. So this is actually just exactly by definition, it's f prime of x. Okay, and then what about this one? Limit as h goes to 0 of f of x. Well, what's happening as h goes to 0? Well, there's no h here. This is completely independent of h, so it might as well be constant. So you should treat it exactly how you would treat a constant expression. So the limit of a constant is just going to be that constant. In other words, it's just going to be f of x. And then finally, what do we have here? It's the same idea we applied over here, right? This gave us f prime. This is going to give us g prime. It's the same expression, just with the function g instead of h, or pardon me, g instead of f. So this is g prime of x. So if we put those pieces together, we can finish it off like this. It's going to be f prime of x times g of x, right? Just take these two and multiply them to get your first term. So I've just written out all of this, but in a nicer form. And then for this term, I'm going to have f of x times g prime of x. Okay, and that actually is the rule now that we're going to use to calculate the derivative of capital F. Right? Remember what capital F was? It was the product of the two functions little f and little g. So really, we're talking about writing down a rule for a derivative of this function, capital F of x, defined by f of x times g of x. It turns out I can't just simply take the derivative of f and then take the derivative of g and then multiply them after. That doesn't work, and it's one of the most common errors in this course. But what I can use is this rule here. So this gives us the product rule, which I'm going to state now once and for all, and we'll put a box around it to identify it as important. So the product rule, if I have the derivative with respect to x of the product of two functions f and g, it turns out the derivative is going to be, I'll use prime notation to write down the right-hand side just so I don't run out of room. So f prime of x times g of x plus f of x times g prime of x. And this is a good rule to put on your formula sheet because you'll need to use this very often. And if you practice writing it out every time you use it, I suggest just writing it out each time you use it, and I'll show you what I mean by that in the next few pages when I do some examples. You can actually memorize this rule really quickly. Like, are you going to have to do this work again? No, you won't have to do this work again. We just need the rule. This is the upshot of everything we did on this page. This is really all you need. But this is the justification for where that rule came from, everything else on this page. Okay, so this rule is going to be one of your best friends going forward in this section.